we're Team Second Wind. We're working on the Incentives Monitor 2.0. I'm Nate Geller, mechanical engineer.
Omar Garibay, mechanical engineer.
Jason Smith, mechanical engineer.
Makana Dang, electrical engineer.
Seihu Joe, computer engineer.
So, as you can see our plot chart here for restoring lung capacity, very few of our concepts and objectives have changed, with only a few exceptions. Our objective to create an incentivized and repeatable device that helps communicate the patient data to doctors reliably has remained the same. We still are partnered with Lung Technologies as well as Northwest Orthopedics. Thankfully, they've been very helpful in this process and understanding their needs for the final product, as well as giving us prompt feedback on the work that we have produced over time. The concept overall still remains the same. We're trying to find the best arrangement of parts and features of incentive spirometers and different OPEP devices to create a final unified product that can at the same time be modular. The approach has not changed overall. We still are aiming for an aesthetic redesign. We're still looking at different OPEP technologies. We have recently discovered more competitors in the market, and we'll be looking at their designs and in their devices to see what's best. What we did change is that we previously had tried to aim for self-regulating valves, such as the check valve system or one-way valve system. The available parts on the market were not really within our desires. If they were air check valves, and they were often small and had very low flow rates. If they were large enough, they were often for water and were far too large for what we needed. So instead, we have created just a simple manual valve to direct airflow between the OPEP module of the device and the incentive spirometer module of the device. Our RPPR analyses have changed a little bit as well. We are aiming to use pre-existing spirometers as a baseline and overall shape and model of the device. Still, we're trying to aim for removable electronics so that we can be testing them separately from the incentive spirometer module. But we are changing this time that we want to try to get experimental with the OPEP pressure of the device. OPEP, with the oscillatory part, there is a lot of room for the rate of oscillation as well as the amplitude of oscillation. So if we can find instruments or any type of experimental method to help get us that information and how our device is performing, we will be looking into that deeply. Analyses have changed a little bit as well. Well, we originally tried to aim for a SolidWorks simulation since they do have a airflow simulation add-on. Through my research, there's been some difficulties in that. We'll touch on that more later on.
Okay, so for our proposed critical path for the MEs, we set out to design the spirometer to improve aesthetics and also allow for the integration of an OPEP device. So we set out to do a bunch of research into different types of OPEPs and figure out which one we wanted to use in our incentive spirometer. We also wanted to change the handle to make it more ergonomic for the incentive spirometer, and we also set out to do like flow simulations to figure out and make sure our incentive spirometer had the correct flow. So we couldn't do that with SolidWorks, so we're now looking into SimFlow software as well as more experimental methods.
In order to tell whether or not the patient has reached the desired volume in the spirometer, in the diaphragm, we will use some sort of sensor to tell if that piston has reached that volume. So I decided, we tested multiple sensors to see which one would work the best for our electrical system. I decided to use an ABDS 9960, which is a gesture sensor, which is able to tell in which direction an object has passed through. So if you say the sensor's here, if you go up, it is able to tell it's coming from the upward direction, downward direction, and so on.
We're also using an LDR. It's a light-dependent resistor. So the LDR will integrate in our circuit, also using a sensor to shine it on the LDR. So this will help us to understand every time the diaphragm goes and disrupts that sensor, senses the LDR, we can get values. And this values, we can take it and make it an output to see whether the patient has successfully made the required inhalation or not. But with that, we also integrated a buzzer. The buzzer will help with the audible alarm. That way, if the sensor is being triggered, the patient doesn't have to look at the screen all the time, or maybe if they are unable to read, they can hear a beep that will indicate that they have reached the actual required level.
I will also incorporate that to the APDS 9960 circuit as well. In order to read and display this information of whether or not they've reached their SMI or sustained maximum inhalation, we will use a microcontroller, and the microcontroller that we decided to use was a Raspberry Pi Pico. And so the way that it'll work is both sensors will read the values to the Pico, and they will send the user through the LCD display and the buzzer whether or not they've reached that SMI. Also, the LCD display and buzzer will notify the user every 5 to 10 minutes when it's time to perform another sustained maximum inhalation. So it kind of acts as a reminder system.
So during testing, we have observed that sometimes using the LDR, when the laser is interrupted using the diaphragm and the spirometer, the Pico picks it up, but it's slow to output on the LCD. Like I said earlier, this delay is about a second or a split of a second, but we would like to figure out ways or research other techniques that we can use to make our code run faster, or maybe to make the microcontroller pick up the message being sent through the LDR much quicker and output it on the LCD. So for the RRPs, for the circuit with the laser sensor using the LDR and the gesture sensor module, we see that we are using the Pico with the breadboard, and for testing purposes, we build a prototype of both circuits. So for the laser sensor circuit using the LDR, we are using the buzzer and the Pico, trying to get a more accurate output from our laser, and also from the spirometer if that laser is interrupted.
And then for my gesture sensor circuit, I actually obtained the module for the APDS 9960 from Adafruit, and I kind of connected it or applied it to the Pico, and it just works like that. And in the future, I actually plan on purchasing the sensor itself and printing out a PCB board and making the circuit.
So what you saw in the video of our RRP spec demo was actually our circuit taking in data and also outputted on our LCD screen. This demo showed that we are able to capture the data using the LDR, and every time that light is interrupted, it takes the data and it will say success on the screen. On the same token, while the patient is waiting or it's inhaling, there is a little bit of message on the LCD trying to encourage the patient, because we want patient involvement a little bit to inhale slowly. This is the message that's being output to the LCD when the patient is trying to inhale. There's a message on the LCD that is encouraging the patient to inhale slowly.
Here's the testing video of our APDS 9960 or our gesture sensor. And the way that this sensor works is it utilizes a IR, LED, and 4 photodiodes. And basically what happens is when you move your hand or an object through or in the direction or in front of the module or sensor, it bounces off that IR light from the object and it detects which of those 4 diodes it reads more, and that's how it tells us which direction that was imputed. So here we tested it with this printed little pin that they use for his mechanical design project. We use that as the thing to move in front to test the module. So here we'll play the video. Here you see when I move the pin upwards, the code outputs up, and it's showing the direction in which it went in front of the sensor. And one of our biggest risks that we were planning of when we were testing this is the spirometer housing is made out of a frosted glass, and we were initially unsure whether or not the spirometer, the gesture sensor was going to be able to read through that glass, because we were unsure whether or not that IR was going to bounce off of the actual plastic of the spirometer. So in order to see or test that hypothesis, we did a testing and we broke apart actually our spirometer in half, and we put it in front of the actual module that you see right here, and we continue to do our testing that we did prior. So here we see that when we move it in front, we continue to get results. So actually, at first when we tested it, it didn't work, but we actually, in this video, are able to tell that we were able to get readings through the frosted glass. So one of our next things that we kind of planned for with this sensor was how far away from the actual housing we would need the sensor to be in order to get the most accurate readings. And in order to detect this or to test this, I did a little test where I tested from 1 centimeter away, 2 centimeters away, and 3 centimeters away. The reason why I didn't take into account for larger distances is because inside the actual electrical housing, there's only so much space that we can have the actual module stay away from the housing, and up to 3 centimeters is what we planned. So when I tested each direction of the sensor, so up, down, left, and right, 25 times, and from this testing, we were able to see that around 2 centimeters is when we got the best readings, and for the direction of up, we had the best readings as well. So the reason why we tested it in every single direction for those different distances is because we were trying to see at which orientation of the module would get the most accurate reading, because in the housing unit, you're actually able to turn or place that module or sensor whichever direction we want, and we could have accounted for that direction with the best reading direction of the sensor. So in our case, up actually ended up being the best direction that the module was able to sense. So we'll actually have our module oriented in the upwards direction. And so one of our biggest things that when we did this test is we see that we are able to successfully get sensor readings through the frosted glass, and that 2 centimeters was our ideal distance away from the housing. So we actually tested the sensor with the spirometer as well. We see this here. We have this testing. And here we have Jason using the spirometer, and the pin in the diaphragm is raising, and it's breaking that plane or volume at which we were trying to get. And we see here that no code output came out. So we actually see that with the spirometer, it doesn't work. So our hypothesis is that it's at which the speed of the pin is crossing the plane that the sensor is sitting on is too slow for it to account for and obtain in the code for the sensor. So our plan right now to attack this and to reduce this risk is to look at different recalibration specifications for the actual module and try and change the code from there.
Okay, so here we have our fourth RRP, which discusses the spirometer dimensions and specifications. So our objective here, given to us by Mr. Kern, was to minimize the footprint of the spirometer. And although it's not very specific, we have an internal goal of keeping the width between 3.5 inches and the height between 10 inches. And although we weren't able to print one out this quarter, as there's just a lot of printing traffic, and as one of the printers are down currently, our SolidWorks graph shows that we are around 7.5 to 8 inches. And this is our model. And the next slide, please. And then our third RRP is the OPEP valve, and the objective here was to have a simple transition in the airflow from the spirometer to the OPEP device. And we modeled this device in SolidWorks, and unfortunately we were not able to simulate airflow through SolidWorks as we had previously thought, as the oscillating portion of our project was too difficult to, or it wasn't in SolidWorks cannot apply those oscillating airflows in our device and make it move. So we had to explore other methods of simulation. Although we did validate this RFP through experimentation, which we will show in the following slide. Here we see our setup is Jason on the right, and he is blowing into the inhalation tube with our OPEP valve right in the middle there. And then we have a piece of paper to show whether or not airflow is escaping outside of the valve. Here we see Jason giving the first inhalation. On the left there we see the piston rising on the spirometer and the paper is remaining still. Now he exhales, see the paper still doesn't move, switches the valve, gives an inhalation and there's no movement in the spirometer. Now he exhales and we see the paper fly back and forth.
The audible spec demo, we observed when we ran the code, what we're trying to do really is just trying to make sure that we have an audible every time the spirometer, when the spirometer interrupts the laser, indicating that the patient has reached the prescribed level. So there's a beep, there's a small beep that's integrated into our code, and also it will show on the display as well. It will show the amount of successful inhalations, and it will also read success on our screen. We tested it, and we were able to achieve that. Another thing we just would like to do during the winter break, as I said earlier, is just to try to make the code just run a little bit faster.
All right, so for our critical design specifications, our first RFP was the proximity sensor. Our objective was to accurately record successful inhalations. And we verified this through code. You also saw it when Colin was demonstrating it in those videos. So this demonstrates the ability to record when the diaphragm crosses the target. Our second RFP was the OPEP valve integration, which was a simple transition from the spirometer to the OPEP. And we verified this through experimental methods by just printing out our valve and switching the flow direction. And yeah, so our third RFP, Jason.
So the third RFP is the alarm system. We might need an adjustable audio reminder for the patient to repeat their exercises of inhalation, as well as not only just audible, but also a visual as well on the LCD screen. We will validate this through the output and code output and testing. While we don't have fully fleshed this out yet, which you did, Seiyu did partially prove this concept through the integration of a speaker in his LDR circuit, in the light detection circuit. When the light was broken, the beam was broken, the code gave a signal to the speaker to deliver a beep, which alerted the patient that they had successfully performed their exercise. Now we just need to further integrate code with a timer function in order to remind the patient that they need to repeat the exercise so many times per hour. And this demonstrates that the internal timer can be kept and that the patient stays on track with what the doctor has prescribed. And lastly, the fourth specification here is size overall. We have goals of about less than 10 inches in height and width of less than 3.5 inches. We're We derive that goal from Kerry Curran's request of us, that he wants to minimize the overall size of the new device. This is just so that when hospitals purchase these and they store them in their storage rooms or whatever, that it will not be too much of an upgrade and won't take up too much extra space as opposed to just a singular spirometer model and a singular open model. Although Curran was not exact in these numbers, he just wants to minimize them. So for clarity, these are more internal numbers that the team have come up with on their own as goals. And the validation is just simulation through our models in SolidWorks. We can take exact measurements of the overall model. So for the different types of engineering analysis we want to perform, we want to analyze the range of the sensors. In other words, more broadly, the distance that they can read. We want to know what battery size we can get away with. Obviously, a larger battery has a longer life, but also takes up a lot more space in our overall device. We want to analyze the power consumption of our components, specifically the Pico, speaker, and LCD screen portions will be drawing the most power. We want to analyze the oscillatory pattern and magnitudes of the LPET device, either experimentally or through software analyses that has yet to be determined based on our research that we performed over the break. But we'll get into that later. The spirometer analysis overall, we need to make sure that the readings are consistent, but we're not reinventing the device. We just want to make sure that our device is ultimately similar to what is already made for us. So we just need to make sure we can replicate and get an approximation to what already exists. We also need to analyze the OPEP integration. This thankfully can be done in SolidWorks as we model each of the parts. When we put them together in assemblies, we can take overall measurements and find out what is the best arrangement and location of OPEP module along with the spirometer housing. And finally, the device and housing design. Again, which is just, again, simply through SolidWorks modeling. We can view our finished product in the 3D view. You get view angles and the overall shape of the device.
All right, for our mechanical engineering analysis. So since we're changing the layout of the spirometer somewhat, it's mostly aesthetics, but we have calculated the pressure required to lift the piston. This is nice to know in case we do end up making more fundamental changes to the spirometer design. We plan to use nanometer next quarter to find more specific data for airflow, but the pressure required to lift the piston is nice information to have now while we're still just designing the aesthetics of the spirometer. All right, so for our block diagram, I'll be talking about the mechanical aspects and Jason will be talking about the electrical aspects. So for the mechanical parts, it starts with the patient breathing in through the mouthpiece and tube. This airflow is led through the valves, which connect to the diaphragm, which is what raises the piston, and also into the ideal flow indicator, which shows whether or not the patient's inhalation is the ideal flow. And then for the patient's expiratory process, through the OPEP device, they breathe out and it will oscillate and clear phlegm from their lungs.
Now here on the electrical portion of the chart, you may notice that there hasn't been much change overall, and there hasn't really been much change, just more development in each of these blocks. For the level sensor, we have two definite paths of sensors that we can have. Seibu has developed the laser LDR-based sensor, and Akana has developed an infrared-based proximity module. For the microcontroller, we have confirmed it as a Raspberry Pi, Raspberry Pico. The reset button that was previously required has been exchanged for a power button now, or a power switch. Memory of the module, the needs have been reduced quite a bit. The The board only needs to keep track of how many inhalations the patient has done over the course of an hour. Since through our talks with Carrie Curran, we have figured out that this device needs only to hold that information for the course of an hour. After an hour is finished, the patient will often be checked by an attending nurse or even the doctor himself. In that case, memory is a very minimal concern, but it is still a component of the overall device. The timer, we no longer have to create a time log of the relative time of, say, 12:30. It's more just a general timer of when the patient needs to repeat their exercise over the course of an hour. The speaker module is still an essential part. The LCD screen has remained the same to remind the patient visually and show their success over time, as well as relay the information of the patient's success to the doctor. And finally, the battery pack also remains the same as well. Makana has discussed different options that we have for battery packs, whether a watch battery module or even a power bank, a rechargeable power bank. It is still all encompassed here in the electronics portion.
In order to power our Raspberry Pi Pico, we plan to have some sort of battery source, and in order to size for this battery, we need to do some load calculations. So first, you notice that our Pico actually runs in 4 different modes. There's a popcorn mode, a Butsa mode, a dormant mode, and sleep mode, and each of these different modes actually have different currents required to make the Pico run. So the 2 modes that we expect the Pico to be running in our situation is the popcorn mode, which will require an average of 86.5 milliamps, while we believe that when we have just it displaying the completed SMIs, or sustained maximum inhalations, we would be in the Butsa mode, which requires a current of a lot less, which is 8.63 milliamps, and both of these will be at 5 volts. So we are actually able to size or figure out what those loads were, and then figure out our battery sizing based on this. And the life cycle that we plan to have our electrical system for the spirometer work is a 2-week period, and we plan it to be running for 70 hours, 60 hours in this popcorn mode or running mode, and 10 hours in this idle just display mode. And like with our calculations, we see that we would need around 10 amp hours, and in order with this, we actually come up with 2 different batteries that we could use. So this first battery is the CR2032WR sub. So this is a 3.6 volt lithium battery, which has 220 milliamp hours. Well, this is a lot lower than the milliamp hours that we would need to run our device. We actually we're still doing research and figuring out if our people will be running on that popcorn mode. And if not, we expect that this might work, but a problem that it might have is really low current that would be running to the Pico, and after some time it wouldn't be able to work as well, and it would make the actual pins dysfunction as well. So another idea that we had that would also make it a lot easier for the user, instead of purchasing expensive watch batteries and replacing it each time, is to actually have a power bank in the electrical system that is rechargeable, so it'll make it last like 2 or 3 years longer than the actual watch batteries that we planned for. And this USB here is 5 volt outputs for at 2.1 amps and 5,000 milliamp hours. This might be outputting too much current at 2.1 amps, but we can use some sort of current limiting device to get the desired current that we want to run the Pico at. So, yeah.
So part of our analysis is to actually create the model in SolidWorks. Here's a quick little animation of the overall device coming together. This portion here is the incentive spirometer with the main diaphragm that measures the volume of intake, and the smaller cylinder here being the flow indicator. The mouthpiece connection is right there, and the larger box coming in is going to be the housing for our moped device, and the smaller portion here is the valve, which was demonstrated earlier through our demonstration video. It all fits together quite well, with a large cutout being made for the OPEP device to fit within the overall body. While it is in SolidWorks, we're able to know the exact dimensions. We can even estimate weight of the device through choosing the material of all our components.
During the winter break, I will be doing more research on how to make the code for the MicroPython on Thony to run a little bit faster. I've realized there is a little bit of a delay on our project in the sense of picking up the spirometer, maybe a second or a split of a second delay, and I would like to mitigate that during the winter break.
So what I'm going to be doing over winter break is doing more research into flow analysis. The SolidWorks method didn't really pan out, so we're looking into other flow simulation softwares, as well as doing like more experimental methods. I'm looking into like flow measuring instruments.
Over the break, I'll be researching potential options for producing our new revised spirometer. One of the problems we continue facing is how we will show our end product, and the 3D printers currently can print clear filament. So looking into different molding options or just any different production models that we could potentially come up with between winter quarter and spring quarter is what I'll be researching over the winter.
Over the winter break, I'll be writing up a proposal for the school to purchase a SLS printer. Omar will be studying methods to produce our housing in here and now. I would, with the help of Ken McPeak, write a formal proposal for the purchase of an SLS printer. This will help the school overall in the production of very refined and precise different types of 3D printing. And the full document will be received by faculty sometime in the middle or end of winter break.
So since the APDS 9960 wasn't able to tell when the piston surpassed the actual sensor, I will be doing research calibration on the APDS to see how to set it for different speeds so it's able to tell when the piston is crossed. And I will also start updating and making our website for our project.